All right. So first, I'd like to thank Dr. Ruhi and Dr. Wong and the other organizers for the invitation. So my presentation is really about trying to bring some of the capabilities of building specific performance-based assessment to the regional scale. So the automation, optimization, and distributed computing; those are just some of the tools that we use to make that happen. There's also some machine learning in there, but I try to keep my presentation titles to a 5 buzzword maximum. So I think I've reached that maximum. So we don't have the machine learning in there. So why do we want to do that? Well, it turns out that there are some questions that you might want to ask about risk and resilience at the regional scale that sort of require these building specific capabilities. So I'll talk about a little bit about that as well. So before getting into it, I want to talk a little bit about the NERI Sim Center, with which I'm affiliated. And as you'll see later, it's some of the tools that are developed by the Sim Center enable the type of research that I'm going to talk about today. So the NERI Sim Center is part of a set of NERI funded facilities that include cyber infrastructure, field reconnaissance, and things like that. So the Sim Center application framework is really built on the performance-based engineering principles, where you try to link these different modules together in terms of hazard, structure response, damage, and losses, but also trying to connect that to recovery and other broader issues. And a central part of that is quantifying uncertainty and propagated uncertainty throughout the different stages. Now, a lot of these performance-based principles were developed in the earthquake engineering community, but the Sim Center is really trying to broaden a lot of those to other types of hazards, as we'll see later. So, as I mentioned before, again, a lot of the simulation workflow is built on these performance-based principles. But a big part of what the Sim Center is trying to do is try to scale those ideas up so that we can start answering questions about risk and resilience at the regional scale. So there are tools and models that are associated with some of these different stages. So, for example, in describing assets, part of the goal is to have high resolution building inventory in these regional assessments. And so there are tools that are currently underdeveloped and also being used to allow that. This is one example, Braille's building recognition using AI at the large scale. And so the idea here is that using images of buildings and some computer vision techniques to try to fill in missing pieces of information in terms of inventory and other features that are needed for these risk models. In terms of the hazard characterization stage, as I mentioned before, so this is a multi-hazard simulation framework. So there are tools that are being developed, and a lot of these tools are built on top of tools that have been developed by different agencies around the country. So, for example, for hurricanes, they're building on top of some NOAA tools. For earthquakes, tools developed by USGS, such as OpenSHA, OpenQuake, and also the SCEC Center for utilizing simulated ground motions, right? So a lot of what the Sim Center is doing is pulling a lot of these tools together under one platform and making them usable for researchers and other folks. Another sort of part of the performance-based framework is simulating structural response of different types of facilities. And so again, there's a lot of work going into taking experimental data, using them to calibrate component level models to be able to simulate structural response under different types of loading. So there's one example here for wind based on some wind tunnel tests, and also for earthquakes using some shake table tests to calibrate a structural model, in this case for a wood frame building, I believe. So in terms of damage and recovery, so the performance-based earthquake engineering framework was sort of published as a set of guidelines, FEMA P58. And there's also the HAZUS framework, which was developed by FEMA, which is done at a lower level of precision. I'll talk a little bit about that in a little bit in detail in a little bit. But again, the idea is to bring these tools together and allow comparative analyses using these different types of damage and loss assessment tool, and also trying to keep in mind things like population demographics, the need for financing to facilitate recovery, availability of workforce. Again, all of these issues that need to be tackled when you try to scale these assessments up at the regional level. So again, the vision here is to facilitate these high-resolution regional simulations and try to establish a connection between the building-specific or local simulation and these regional simulations. So this slide just gives an overview of some of the tools that have been developed. So at the lowest level here, these are some of the software modules. So, for example, for uncertainty quantification, there's the COFEM software, where they use quantified uncertainty with optimization for finite element analysis. In terms of hazard-specific structural response, there's EEUQ, which is focused on structural response to earthquake ground motions. There's WEUQ for wind and HydroEQ for tsunami and storm surge. And then for assessing performance at the individual asset level, there's the PBE tool, and all of this is sort of housed under the R2D tool, the regional risk and resilience determination tool. Okay, so now I'm going to talk a little bit about the research that we've been doing, again, to try to understand how to scale up some of these building-specific performance assessments to the regional scale, and also thinking about what are some of the questions that really necessitate this type of scaling. So the specific focus is going to be on evaluating alternative seismic design procedures through regional scale assessment. So there has been, I would say, within the last decade or so, a national push to advance our building codes beyond the life safety performance objective that it's been known for historically, right? So historically, when you do earthquake design of a building, the intent of the building code is to minimize injuries and fatalities in the likelihood of a major earthquake. And in recent years, there's been a push to move towards more functional recovery-based design. So thinking not just about life safety, but thinking about the extent of damage and whether a building is usable after an earthquake, whether it's repairable after an earthquake, and thinking about the time that's needed to achieve its intended function, right? Now, there's been a lot of work going on to try to evaluate different types of alternative design procedures to enable these functional recovery performance objectives. But a lot of it has been done at the building specific context. So maybe looking at a set of archetype buildings and trying to understand how the performance of these buildings change with alternative design procedures. But all of this is done outside of a regional context. Now, what we believe is that examining the implications of these modifications to meet functional recovery performance for specific regions, it is beneficial, especially for large urban centers with high seismicity. So San Francisco, Los Angeles, where I'm from. Now, to be able to do that, this requires high fidelity and high resolution assessments. And the reason is because these design changes are done at the building specific level. So for example, changing your importance factor, changing your R factor, your response modification factor. These are the types of changes that are being examined to try to achieve these functional recovery performance objectives. And you cannot really evaluate the implication of these changes using the traditional, say, HAZUS model, because these types of factors are not built into the typical regional HAZUS simulation. Now, these high fidelity, high resolution assessments comes with computational challenges. And so, as I mentioned before, a lot of this work is trying to get over some of these challenges so that we can start asking these questions at the regional scale. So this work is part of a broader effort to evaluate these alternative seismic design procedures at the regional scale. So if we look at least on my right end, on the right end in general, we want to be able to evaluate these functional recovery-based design provisions. And to be able to do that, we need to be able to do what I call hi-fi. So that's the high fidelity, the high resolution is implied. And then fully mechanistic regional assessment. The fully mechanistic there just means we're not going to use any type of surrogate models or any type of shortcuts to be able to do the assessment, right? And so in doing so, there are some intermediate steps that are needed. So if you're going to do these high fidelity assessments at the regional scale, there are some differences when you start aggregating the performance and assessing risk. There are some differences there are some things you're going to have to do different relative to, say, the traditional hazards approach. So that's one of the things we've worked on. And then once we're able to do that, try to implement it on a large scale and try to understand some of the benefits, the trade-offs, some of the challenges. And then keeping in mind, when you start talking about evaluating alternative design procedures, this is an iterative process, right? So if you have to iterate on these procedures, maybe you don't want to have to perform the high fidelity assessment for every iteration. So that's where we started evaluating sort of some more efficient strategies for these regional assessments. So today I'm just going to talk about 3 of those things. But before I do that, I want to start with some definitions. So I threw out some words there earlier on, and some of these words are understood differently by different people. So I want to make sure we're sort of all on the same page when I'm using some of these words. So when we talk about resolution, we just talk about the level of detail that we use to model the asset. So for example, are we talking about a site-specific hazard and performance assessment, or are we doing something like what's done in hazards, where you would aggregate a set of buildings at a certain spatial scale across some geographic unit? So when we talk about high resolution, we're talking about doing building-specific and site-specific assessments. Now, when we talk about fidelity, that means the level of detail that we're doing our structural model and our performance assessment, right? So for structural modeling, we can use a single degree of freedom system to represent our building structure. We can do what's called a simplified MDOF, where we do a single degree of freedom per story, or we can do a detailed 3D multi-degree of freedom system. So when I talk about high fidelity, I'm talking about the 3D multi-degree of freedom system. Okay, so I also talked about fully mechanistic regional assessment, right? So when I talk about a mechanistic assessment, I'm just saying that we're using an explicit analysis and performance assessment model, right? We're not using any meta models. We're not using any surrogate models. We're doing everything explicitly. And a surrogate model here just represents some type of compact statistical representation of that mechanistic model. So it can be done using a machine learning model or some other type of simplistic model. And so if we are going to use a surrogate model, one of the things we have to think about is within this FEMA P58 framework, where we have hazard, structural response, damage, and loss, we have to think about at what stage of that assessment do we want to inject the surrogate model if we are going to use it. So that's something we also have to think about. So how did we arrive at this hi-fi FMRA? Well, we want to do a regional risk and resilience assessment. We can think about how to address both the level of resolution and the level of fidelity. So fidelity, again, the high fidelity means we're doing detailed 3D structural modeling and component level analysis for a performance-based assessment. And at the low level of fidelity, we can utilize a surrogate model. And then for resolution, we're thinking about how do we represent our building granularity as well as our hazard, right? So again, for the building or the hazard, we can start aggregating things at different spatial scales. So when we talk about hi-fi fully mechanistic, we're doing building-specific characterization and hazard characterization, and we're using these high-fidelity models. So to demonstrate some of this, I'm going to use a case study involving the city of Los Angeles. So what we want to do here to start with is to implement the hi-fi FMRA approach to assess the distribution of building-specific and aggregated losses and functional recovery times at the regional scale. And then again, as I mentioned before, if we want to do these alternative design procedure evaluations iteratively. Maybe we don't want to do the hi-fi high-res each time. So we have some alternative approaches that we've been looking into that are specifically for those iterative assessments. And again, the target location is the city of Los Angeles, and we're focused on 1 to 4 story single and multifamily residential buildings. And the inventory size we're dealing with is on the order of about 15,000. Okay, so this is the framework we're using for the hi-fi FMRA. So there's a lot going on here, but the good thing is that it's numbered. So I'll sort of walk you through each of the stages. The first step is just defining the inventory, the target region and the inventory. The exposure modeling. So the thing about the exposure modeling that's different is that we are actually evaluating design procedures. So we actually have to perform designs at these different locations as part of this workflow. And I'll talk about how we're able to do that. But to do that, we need building and site parameters. For the seismic hazard modeling, we can look at that in a couple different ways. We can do what's called a scenario-based assessment, where we take one or a small set of scenarios and evaluate the performance at the regional level. We can also do what's called a stochastic event set assessment, where we look at all the possible events that can significantly affect the performance of the inventory in the region. And then we consider the rate of occurrence of these events, and we can start to quantify performance in what we call a time-based approach. So look over a period of time and quantify the likelihood of meeting some performance criteria over that period of time. Step 4. So again, in step 4 there, we're modeling each building and site individually, and we have over 15,000 buildings. So we don't want to, because of the computational expense that's involved, we don't want to have to do any redundant performance assessment. So what we're doing is we're first filtering any redundant building and hazard pairs. So if you have any 2 sites that have the same, I'll call it building variant. I'll explain what that means in a little bit. If it has the same building variant and the same site characteristics, then we're just gonna call those things one, because the high fidelity assessment will give us the same result in any case. And then, so once we have that, we'll do our design and performance assessment, and that's where the automation and the high performance computing comes in, and I'll talk a little bit about how we're utilizing that. And for the results, we want to get the full distribution of performance metrics. So this would be repair costs, and this would be functional recovery at each site. Okay, so I mentioned before this idea of a design variant, right? So we have 15,000 sites. We are doing designs as part of this workflow. And so to do these designs, we're actually placing these design variants at the various site locations. So you can think of a design variant as like a skeleton of a building. So these are parameters that define the building, but before the building has actually been designed, right? So things like the floor layout, the number of stories, the type of panels. Again, we're dealing with wood frame buildings, the seismic weights, right? So each of these would constitute a variant, but you still have to do the design process to actually get a building design. So for the exposure modeling, what we do is we would randomly place those variants at each site. And we have a tool that I'll talk about a little bit later, Wood SDA, to automate that design process. And we would repeat this for all 15,000 sites or so. For the hazard simulation, I'm going to talk a little bit about the stochastic event set hazard modeling, because that's the more complex and computationally expensive one. So we're doing this using R2D, which is one of the SimCenter tools that I mentioned earlier. And the start of that process is generating a set of an earthquake catalog using USURF3, right? So USURF3 basically gives us, again, all the events in the region that could have an impact on our infrastructure. But we don't want to use, for example, in this case for Los Angeles, we're talking about on the order of hundreds of thousands of events, right? So we don't want to use all of them, because again, there's a computational burden there, but we do want to get results from the performance assessment as if we have used all of them. So to do that, we actually use some optimization-based approaches that have been developed by previous researchers to downsample the number of events. And for each event, we need a set of correlated ground motion maps. So basically the joint distribution for a given event. We need a joint distribution of shaking at all the different sites represented in our inventory. And to consider the uncertainty in that joint distribution of shaking, we're generating multiple maps per event. And so we're also downsampling the number of maps. So we're doing high resolution, high fidelity. So that means for our performance assessment, we're doing nonlinear response history analyses, which means we need to do site-specific ground motion selection for each of these 15,000 or so sites. So what comes out of our stochastic event set assessment is a set of maps that give us the full response spectra, because again, we need to do ground motion selection at each site. So a full set of ground motion response spectra at each site for each scenario, and then we're downsampling that from 80 maps to 60 maps, meaning we're using 60 ground motions to represent that uncertainty in the shaking intensity at a given site. Right, so the plot on the right is an example for a single site where it's showing the target spectra and it's showing the selected ground motions and how the median of the selected ground motions match the target. Okay, so I mentioned before that as part of this whole workflow, we are actually doing designs. We want to be able to evaluate alternative design procedures, so we need to include the design process in our workflow. And to be able to do that, one of my PhD students developed this tool we call WoodSDA. It's a Python-based automation tool. So what it does is it takes in information about the building and about the site and information about the ground motion, and it gives us output all of the types of performance metrics that we want for our regional simulation. So for example, collapse fragility, the probability distribution of losses, the probability distribution of functional recovery. And so internally, there are 4 modules. So one module actually does the design per ASC 7 and all the various standards that are used to design wood frame buildings. The next step is to build a structural model. So again, we're building these detailed 3D nonlinear structural models in OpenSeas. All of that is automated. So once the design module is finished, the structural module takes that information and generates an OpenSeas model. And then remember, we're doing part of the high fidelity is we're doing component level damage assessment, right? So we're evaluating repair costs and we're evaluating functional recovery time. And we're doing that by starting at the component level, simulating damage at the component level, and then we're aggregating that to the building level and obviously, again, up to the regional scale. So we have that damage module that takes the responses from the structural model and converts that to component level damage. And then finally, there's the loss module where we're using some of the SimCenter tools again. You see there Pelican. This is a tool that sort of builds in the FEMA P58 performance-based assessment framework. You also see ATC 138, which is a functional recovery methodology. So our loss module also embeds that particular tool into the workflow. Okay, so we do all of that. We do that at the regional scale. And again, we're doing stochastic event set assessment. So we're sort of doing a probabilistic assessment across all the different scenarios that can affect the region. And so this is one type of result that you can get for this. So this is a loss exceedance curve, a regional loss exceedance curve. If you haven't seen or used these before, they can be sort of cryptic. The horizontal axis here is the total repair cost for the region. The vertical axis is an annual rate of exceedance related to modeling things using an exponential distribution. But I think from sort of a communication standpoint, what's most valuable is that you can get an estimate of the total losses for the region for any given hazard level. So for example, here, I'm showing here for the 475-year return period, the total repair cost is $7 billion. For the 75-year return period, we're looking at $10 billion. The other thing we can do is because again, we're doing these performance assessments at the building level, so we can actually look at an exceedance curve, in this case for functional recovery at the individual building level. So the one on the left looks like a big cloud, but it's basically individual gray lines for each of the individual buildings. So it's basically the distribution of functional recovery time. And if we take a horizontal slice through that corresponding to a particular hazard level, in this case, the 475-year return period, we can start to map the distribution of functional recovery times associated with that particular hazard level. The other thing we can do, again, because we're doing component level assessment, that's part of the high fidelity thing, we can look at what components are actually driving, in this case, our repair costs. So one of the things we can do is we can say, okay, let's look at, and these are, this is a large Monte Carlo simulation, so a lot of it is probabilistic. So if we look across all the realizations, we can look at the top 10 drivers in terms of components of repair costs. So we're seeing here that the exterior walls, the fixed partitions, the wood light frame, those are the things that are driving a lot of the repair costs. But there are other components as well, like the stairs and the chill water systems that are contributing significantly. The other thing we can do, we can look at these component level drivers at the regional scale, right? So we can look at how these component level drivers are distributed across the entire region. And so again, the green dots you're seeing dominating here, those are the exterior walls, and then the light blue are the partitions, and there's some other colors that are mixed in there. Okay, so what we just went through is the process of doing this hi-fi FMRA, again, high fidelity, fully mechanistic. We're not using any surrogate models, but again, we are trying to understand the implications of making changes to the design procedure on things like functional recovery and repair costs. So that's an iterative process. And so because we don't want to have to do that hi-fi for each iteration, we started looking at different strategies, different efficient strategies for going through that process. And so the strategies are built on playing with the resolution and fidelity, right? So as I mentioned before, you can start aggregating buildings, spatially aggregating buildings and hazard. Or for the fidelity, you can start using simpler structural models, or you can start using surrogate models. And so based on those things, we came up with different strategies that are based on these sort of two things, either that aggregation or using some type of surrogate model. And I'll talk about them in a little bit. So what I'm showing here is I'm going to show sort of two alternatives that are both high fidelity, but we're playing with the resolution. So what you're seeing here is the high resolution. So that's the one that I just went through in a second. Here we're calling this medium resolution. And so what we're doing here, we're aggregating things, but we're aggregating them before we actually do the design. So what we're doing is, we're looking across the region and we're looking at the design intensities. And instead of doing a design for each individual intensities, we're binning these design intensities. And if a set of buildings fall within that bin and they have the same design variant, then they're going to have the same design, right? So that's one strategy that we're using. The other strategy we're calling low resolution. So it's also doing aggregation, but it's doing it in a different way. So now we're doing sort of a spatial aggregation, right? So for the medium resolution, there is some spatial aggregation because the design intensities are spatially correlated. But for the low resolution, we're just looking at things spatially. So we're looking at spatial clusters and we're grouping them. And for a given variant, if two sites have the same variant within that cluster, then they're going to have the same designs. So those are two strategies, again, that involve, we're still using these high fidelity models, but we're varying the resolution. And then the last one is the surrogate-based assessment. So you can think of that as a low fidelity model, but we can actually do a high resolution assessment, meaning we can actually still look at performance at the individual building level. So a quick overview of the process here. So we take some data from the fully mechanistic assessment and we use a machine learning model to build our surrogate. Again, one question we have to ask is, at what point in that 4-step process, hazard, structural response, damage, and loss, at what point do we sort of inject that surrogate model? So one option is to do it sort of in the most computationally expensive phase, which is the structural response. and then you would do everything else explicitly and get your building specific losses. The other approach is you can just predict the consequences directly. So you sort of bypass all three. The last three of the mechanistic steps, you would bypass those with a surrogate model. So we explored both of those. There are some challenges associated with the structure response one that in the interest of time, I don't have time to get into. So today I'm just going to talk about the surrogate model where we're just predicting the consequences directly. So a little bit more about the surrogate assessment. So again, we're taking in information about the building, about the site parameters, the shaking intensity, the design intensity, things about the soil like VS30, and we're predicting the empirical distribution of a particular performance metric. So this could be the loss ratio, this could be the functional recovery time. We're actually using the hi-fi low resolution data, and the point of that is we're actually using a subset of the data from the hi-fi fMRA, so that can give you a sense of some of the computational savings that we can get from that surrogate model. And the predictive engine we're using is XGBoost. Nothing particularly interesting about that. It's a sort of a workhorse in the machine learning community, if you will, used for a number of different problems. So one of the things we have to do is we have to evaluate these strategies, right? So we want to evaluate how well they stack up against the hi-fi fMRA approach. And so we did this evaluation at multiple scales, right? So the first scale is at the regional scale. So when you sort of aggregate all of the losses at the regional scale, how do these models stack up? And so what we're seeing here is that up until if you start at sort of low return periods, up until sort of the 1400 year or so return period, we're actually getting a pretty good match with all three of the methods. And it's at that 1400 year return period that we start seeing some divergence, particularly the low resolution model starts to diverge significantly in terms of the mean annual rate of exceedance associated with a particular inventory loss. And then at the 5,000 year return period, that's where you start seeing deviation between the surrogate and the medium resolution. They start deviating from the high resolution model. So that's at the regional scale. I also talked about looking at things at the individual building level. So again, we can look at these loss exceedance curves for individual buildings, and we can create this map, in this case, showing the spatial distribution of losses for the 475 year return period. And we can do that at the building level. So let's look at how the efficient approaches stack up when you look at the distribution across entire buildings, right? So this is just a kernel density showing the distribution of building-specific repair costs and how the high-resolution approach compares to the other three approaches, right? So you see at the building level, there's some significant deviation there. For example, if you look out at the tail of that distribution, so the higher repair costs, the sort of efficient models, if you will, don't perform as well. And then if you look at the performance across the three models, we actually see that the surrogate model gives us the best performance. And why is that? So remember I said for the med-res and the low-res, these are high-fidelity models, but we're sort of giving up. We're sort of losing out on some of the resolution through that aggregation. Whereas for the surrogate model, it's a low fidelity model, but we're still able to do these high resolution assessments. So we're doing a little bit better at the building level with the surrogate model. Here, we're now aggregating things at the neighborhood scale, right? So we're taking the building specific losses within a given neighborhood, and we're adding that up, and we're looking at the distributions. And so we're comparing those neighborhood level losses, the hi-fi, the one on the upper left, to the three others. And actually what we're seeing here at this scale, we're seeing that the surrogate model still performs well. But one thing that's interesting we're seeing is if you compare the medium resolution, that's this one, to the low resolution, that's that one, the low resolution one actually performs better. Right? And that might seem counterintuitive, but the reason is if we go back to sort of how we set up that low resolution model, we actually did explicit spatial clustering for that model. So I believe that spatial clustering actually helped when we were looking at the performance at the neighborhood level. We can also do a comparison on sort of the component level drivers. So remember I said one of the things we want to look at is which components are actually driving the losses, which components are driving the functional recovery. And so here we see for the medium and low resolution, they're actually doing a pretty good job. I mean, there's a lot of green there, so the differences are kind of subtle. You sort of have to squint to see it. But in general, the medium and low resolution are doing quite well in capturing those component level drivers. The medium resolution one is doing a little bit better. Okay, this slide just gives an overview of some of the computational expense comparisons, right? So this hi-fi, high-res assessment, because we're utilizing automation, because we're utilizing high-performance computing, because we're utilizing optimization, we're taking an assessment that would typically take on the order of weeks to months, and we're doing it in like 45 hours or so. And then you can see as we go to the medium and low resolution, we start to save even more on the computational expense. Okay, so to wrap up, just really quickly to give you a sense of how we can use these results to evaluate these different design provisions. So what I'm going to do is just a quick sensitivity. What I'm going to show is just a quick sensitivity study where we can play with the importance factor, right? So this is a factor that determines the base share that you use to do your seismic design. So we want to play with that importance factor, which is related to the structure itself. That's the IE. And then we also use a component fragility adjustment factor. So that's the things that are going to, that IP is going to affect the performance of the non-structural components. And then we ran a series of cases. So what we're showing here is for a single IP, so we fix the non-structural performance or the non-structural design, if you will, and you look at the effect of the importance factor, so the designing for higher and higher base share. And so there are a couple things here. So so one thing we see is that at lower loss levels, we're actually seeing that increasing that importance factor actually gives us the opposite to what we want, meaning the losses are actually increasing. And so why is that? The reason is that at these lower hazard levels, if you will, it's actually the acceleration sensitive components that are driving the losses. And with these acceleration sensitive components, when you increase the importance factor, you increase the stiffness, you increase the acceleration, and so you're getting greater losses. But as you move further out to the higher hazard levels, then you're getting the type of performance that you want, where you're reducing your losses for a given return period. Another thing we're seeing is that we're sort of getting the return on investment, if you will, is reducing. So for example, the benefit you get from going from an importance factor of 1 to 1.5 is better than going from 1.5 to 0, if you will. So there's this sort of loss of as you go to higher and higher importance factors, there's sort of a loss in terms of the return on investment. And so on this slide, what I'm going to look at is the influence of these fragility adjustment factors. Again, these affect the non-structural components. And so what we're seeing here is that, so for a given plot, if you will, it's a single importance factor. So we're fixing the base share, and then we're changing this IP factor. And so you're seeing the benefits of doing that, and you can see how that benefit changes for different importance factors, meaning as we increase the base share, right, you can see how the benefit provided by strengthening the non-structural components is provided. And this last slide just looks at how those two things interact together. Again, if you compare, for example, on a given plot, if you compare the green to the orange, that tells you how things change when you're increasing the base share, and on the horizontal axis, that's the fragility adjustment factor. So you can look at how things change going from 1 to 1.5, and how it affects both the loss ratio as well as the functional recovery time. Okay, so to wrap things up, some key takeaways. So, the NERI Sim Center does a lot of things. I couldn't get into all of them, but my focus here today was the fact that it develops these tools that bring these building specific performance-based capabilities to regional earthquake simulations, right? And why is that important? Well, now we can ask questions at the regional scale that require these high resolution, high fidelity assessments. And so here we focus specifically on how these tools can be used to investigate issues related to advancement of functional recovery-based design codes. We looked at various strategies for trying to do this efficiently, again, recognizing that there's some iteration involved in evaluating these alternative design procedures. And we found that the relative performance, how these different strategies perform relative to each other, is highly dependent on the scale at which the results are aggregated. So, for example, again, we saw, if we look at the individual building scale, or if we look at the regional scale, then the low resolution model doesn't perform as well. But if we start looking at the neighborhood level, the low resolution model actually outperforms the medium resolution. And that has to do with the spatial clustering that we use for that low resolution model. And with that, I will end. Thank you.
Thank you, Dr. Burton.